Okay, so we have come back to again group theory exercises from Lee. So let's see this next one. Here G is a group of prime power order. That is a finite group of course, whose order is p to the power n, where p is a prime number and n is a positive integer. This type of groups have a name also. They are called p groups. Any such group is called a p group. That means if you have say a group G whose order is 8, then it's a 2 group. Now we have to prove that G must have an element of order p. So let's see how that is possible. Solution. Note one thing in the beginning itself, that n is not 0. That means G is not trivial. The smallest possible value of n is 1 and the smallest possible value of p is 2. Even in that case, G has 2 elements. So that means there will be at least one non-identity element in G in any case. So accordingly, we do not even start by mentioning that G is non-trivial. That is understood. So we start off by choosing an element X in G which is different from the identity element in G. Now by a corollary to Lagrange's theorem, and specifically this corollary, by corollary 3.5, we know that the order of x, of course it will be a positive integer, because our G is a finite group, so every element should have a finite order which is a positive integer. But whatever it is, it has to divide the order of the group. In fact, that's the statement of this corollary. So by this corollary, the order of x is of this form, and since it needs to be a divisor of p to the power n, so it should itself be a power of p, say p to the power k, for some integer k satisfying this. Okay, k cannot exceed n, of course. If that happens, then of course p to the power k would not divide p to the power n. So we need this restriction. Now, if k is equal to 1, which may very well happen, then we are done, because in that case x itself is an element in G whose order is p. So assume that k is strictly greater than 1. It's a positive integer, less than or equal to n, of course, but it is greater than 1. Now we are considering this case. Consider the element y whose definition is this. It is x to the power p to the power k minus 1. Okay. Note that because k is greater than 1, k minus 1 is a positive integer. Fine. So now we are considering this element y, which is actually this. Now we know how to calculate the order of y from a previous result that we have in fact come across, and it is corollary 3.2, which tells us how to calculate the order of a power of an element when you know the order of the original base element itself. So y corollary 3.2, the order of y is equal to this. It is equal to the order of x divided by the greatest common divisor of the order of x again and this exponent, which is giving us the power of x. That means this is p to the power k, because the order of x is p to the power k, and in the denominator we have the GCD of p to the power k and p to the power k minus 1. Because p to the power k minus 1 divides p to the power k, so this itself is the greatest common divisor. That means our denominator is p to the power k minus 1. So this becomes p. So in this case, when k is greater than 1, the element in an element that we are seeking, which has order p, now is y. Y is such an element, and that's it. We are done. So this is the solution. Next, we are in chapter 3, right? And this next one is this, let G be a group having a subgroup H of order 28 and another subgroup K of order 65. We need to show this, that H and K intersect trivially. That means their intersection is this singleton set consisting of the identity element of G. Note that we don't really know whether G itself is a finite group or not, and it in fact does not matter, does not really matter. And if you want to see if that is possible, that is, can you really have an infinite group in which you have a finite subgroup? Of course you can. For example, you can consider the group of non-zero real numbers under multiplication, ordinary multiplication of real numbers. This is a group, we already know this, and we also know that this is an infinite group because the set is infinite. But in this group, you consider this subset consisting of -1 and 1 because it's a finite subset, and you can in fact almost instantly see that this subset is closed under multiplication of real numbers. So by one of the subgroup tests, this is a subgroup, the original group is infinite but the subgroup is finite. It can happen. So we don't really know whether G is finite or infinite, and it does not really matter. We just have to show that these finite subgroups, the subgroups are finite. H is a finite subgroup having 28 elements, K is a finite subgroup having 65 elements. They intersect trivially. Suppose, contrary to what has been claimed, suppose that this is not trivial, that in this intersection there is something other than E. In the intersection, of course, there E would be there. There is no doubt about that because both H and K are subgroups, so each one of them has the identity element. So the identity will be there in the intersection. In fact, it will be there in any intersection of any number of subgroups, finite or infinite. But now, because of this supposition, we can choose an element, say X, which is different from E in H intersection K. Okay. Since H intersection K is, okay, we need not in fact consider the fact that H intersection K itself is a subgroup which is finite, but we really need to use the fact that X is now an element of both H as well as K. That's what we need. So by that corollary to Lagrange's theorem again, what was that corollary? (3.5) Since X is in H and H is after all a finite group whose order is 28, the order of X should divide 28. And similarly, since X is also in K, which is a finite group of order 65, the order of X needs to divide 65. Hence, the order of X, let me write in words, divides this number as well, which is -3 times 65 plus 7 times 28. That means it is 1. Thus, this should be equal to 1. Because it is dividing 1 and its order, so by definition it is any order by definition is a positive integer. So the only positive integer dividing 1 is 1 itself. Thus this is equal to 1, which is a contradiction. And what is it that this statement is contradicting? It is contradicting our choice that x is not equal to e. We know that in any group, finite or infinite, whatever, no matter what the type of the group is, the identity is the only element of order 1. A non-identity element cannot have order 1. That is the contradiction. So, our supposition is wrong. And that's it. That means its negation is true, which is this, the claim, and here the solution ends. In case you are wondering how one can find these integers -3 and 7, you just note the fact that we have used this result, that the GCD of 28 and 65 is 1. In order to calculate this GCD, what we did, we applied the Euclidean algorithm, where you would say divide 65 by 28, you get a remainder. You then next divide 28 by that remainder, and you keep on doing this divisions until you get, or till you get a zero remainder. The last non-zero remainder is the GCD, and that GCD turns out to be 1. You then use these division equations and run backwards to obtain these integers. Okay, if you know that process, you know it. So that's how one can find that you can express one as a linear combination of 65 and 28 with coefficients which are integers. So that's how we have this thing. Okay. So anyway, let's now move on. Next, let G be a finite group. So in this one, it's given that G is a finite group having an element of order k for each k between 1 and 10, with 1 and 10 included. I need ink. I forgot to refill before starting the video. What is the smallest possible order of G? Show that a group of that order exists having this property. Okay. That means what we are given is that there is the finite group G in which there are elements of orders 1 of course it will always be there, that is the identity element, but we also have elements in G of order 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now with this condition, what is the smallest possible group G? I should not say the smallest possible group because there may be multiple such groups, but what is the smallest possible order in this situation? And then we also have to show that there actually exists one such group with that smallest order. Now, since G has elements of orders k, where k satisfies these inequalities, we have again by that corollary, the corollary to Lagrange's theorem, k should divide the order of G for each such k. In other words, G is a common multiple, not G, but the order of G is a common multiple of all these integers from 1 through 10. So with that condition, what is the smallest possible order? That is just literally the least common multiple. Okay, because we already have got the order of G as a common multiple of all these k's, and we also want it to be the least possible, so it is the least common multiple. That's just it, literally that's what it is. Hence the smallest possible value of the order of G is the least common multiple of the integers k with this, these are the integers, and this value, of course it has a definite value. This value is this number 2520. Okay, but how do you calculate the LCM of this many numbers? You can of course use a traditional method that we always use. However, there is an easier technique. Say you want this, right? So what you do, you consider the prime powers that are appearing in these integers. 1, of course, it will just simply vanish in this process. It does not in fact contribute anything. But we have the prime 2, 3, these primes we see among these numbers. These 4 primes we see. Now what is the largest power of 2 that is appearing in these numbers, in the sense that it can also appear as a factor. In this case, however, it is appearing as one of the numbers themselves, 8. So you take 8. That's the contribution of 2 to the LCM. And once you take 8, you do not have to think of the lower powers 2 and 4, because already they are dividing 8. 8 has already become a common multiple of 2, 4 and 8. 8 is in fact the least common multiple of 2, 4 and 8. Okay. Then you look at the powers of 3. What is the largest power of 3? 9. So you take 9. Then we have taken care of 2, we have taken care of 3, then 5. What is the largest power of 5 that is appearing in these numbers? Note that 5 does not appear in the first 4. It also does not appear in these 3, but it appears here once as just 5. Here also there is no 5, but here we have 1 5 as a factor, but still it's there, 2 times 5. So 5 just appears as 5, because the highest power of 5 in this situation is 5 itself, not any higher power, 5 square, 5 cube, those things are not there. So 5 and similarly 7, because in this case among these numbers 7 just simply appears here. The next multiple is 14, which is not here. So this is your number. Okay, fine. But is there a group with this order, and not just with this order, but in which you also have all those elements of all the possible orders from 1 through 10? Yes. Consider the cyclic group finite cyclic group whose order is 2, 5, 2, 0, where you know that this is generated by the generator 1, where your 1 is of course just 1, but the operation, the binary operation, is addition modulo 2520. So the order of 1 as an element in this group is 2520. And you know that in a cyclic group, if you get an element, what I am trying to say here is this: in a cyclic group of some given order, if you get a positive integer that divides the order, then you will get a unique subgroup of that order. This is something that we already saw back in the section on cyclic groups. But we also know that every subgroup of a cyclic group is itself a cyclic group. So for example, say you consider the integer 10. 10 divides this, which you can just simply see. So that means from those results on cyclic groups, this cyclic group has a subgroup of order 10. Now that subgroup, being a subgroup of a cyclic group, is itself cyclic. So that means it will have a generator whose order as an element is 10. So that's how you get an element of order 10. Similarly, you will get an element of order k for the remaining k's. And in fact, you will get elements of many other orders. So that part I just leave to you. You just have to mention that. So here the solution ends. And let's solve one more. $359. But in all these things, whatever I do, I'm again repeating, and I will keep on repeating this again and again. It does not matter that whatever you see here, you should just simply follow these things blindly. You see, if you ever come across something that is wrong, or somehow there is, it's not really clear how something is true, then you please let me know, because that way I will also learn. If you do not correct my mistakes, then it will just simply go on like that. So it's in fact a learning opportunity for me, maybe more than it's a learning opportunity for you, because I am trying to actually learn from you. You just view it that way. Let G equal to this be an abelian group. And it's finite, we can just see that. And it's also mentioned explicitly, abelian group of order, odd order. Let me write that odd here. Odd order K. That means K is an odd number. Show that if you take the product of all the elements, then you should get the identity. Why is that so? Two things are given. K is odd. G is finite, of course, that is also there. K is odd and the group is abelian. So I am going to write a short solution, means the solution itself is short. I am not going to elaborate too much. I will say things verbally, but I won't write much here. I will just simply write this. Since the elements of G can be paired up like this, where A belongs to G, and since G is abelian, we have this equal to E. But how? And in fact, what is this? Let's try to understand that. What I am saying here is that since the elements of G can be paired up like this. That is, we are pairing up an element and its inverse. Since that is possible, and also since G is abelian, so the square of this element should be E. How? You see, when you look at this thing, this square, what is it actually? By definition, it is in fact this product. Now next what you do, next you just take one element and right next to the element you take its inverse. You shift the inverse of this element from here, wherever that inverse is lying, you shift that inverse from here and put it next to the original element. So that means this thing will look like this: A1 inverse, A2 inverse, AK inverse. But there are some doubts about this step. There is of course no doubt about the existence of these inverses here, because these are in fact all the elements of G, and we already know that in a group any element has its inverse. So in fact for each AI here we would find AI inverse here. But the doubt is, are we going to, there are two things, okay. We are never going to run out of inverses because every AI should have an inverse. But will there be any leftover elements here? Say, even after taking all these inverses, maybe there is some AJ that got left out. Because you see one thing, A1 we don't really know what A1 inverse actually is from here. It may be some AI, some AJ. We don't really know what that I or J is. So after making these pairs, we don't really know whether we should have some leftovers or not. Say there is a leftover, say that is AJ. Okay. Originally AJ already is here and its own inverse is AJ inverse, and that AJ inverse may not be equal to AJ. So this AJ got left out. But actually that will never happen. Let me tell you why. Because you see, AJ itself has its own inverse because it is also after all an element of G, and that AJ inverse will appear among these first elements, and that AJ inverse here is it is present somewhere. It also has to be paired up with its own inverse according to this process, right? And its own inverse is AJ inverse inverse. But we already know that AJ inverse inverse is nothing but AJ. So nothing actually will be left out. Once you pair up all the things, you will in fact have finished this part entirely. Okay, this part entirely will vanish after the pairing up process is completed. And now when you look at this product, it's just a bunch of E's, that is identity elements. So that means we get E, and this shifting is possible because G is abelian. Otherwise this may not be possible. Okay, so that's how we are getting the fact that the square of this element is E. Square of this product is E. But now let me keep that part for some time. You may think that why not make this such a complicated argument? It looks complicated, but actually it is not a part of the original solution. The answer to that is of course choice. There is a lizard in the room somewhere. Anyway, let's just ignore that. So the inclusion or omission of this part is up to you. If you want, you can make it a part of the solution. I'm just simply deciding to not make it a part of the solution, because this is something that is, you will see that there will be many occasions in which you will have to pair up elements, group elements or ring elements, anything like this, so that after some point of time you will see that this is actually a standard procedure. Then you yourself would want to exclude such things from your solutions. But if you feel like you should include it first couple of times, you can do it. The only thing you should keep in mind is that you should not exclude anything crucial, in the sense that if you exclude something crucial, it feels like actually there is a gap in the solution. That we should not do. We should not suppress crucial information. But now we are here. Hence, but we also know one more thing, that if we have an equation like this, then the order of this product, not the square entirely, but the order of this product should divide the exponent. This is also something we know from the results and orders of elements. Hence, this should divide 2. Okay. Now, is this order, okay, so that means what? So this is one thing. Just from this we cannot conclude anything definite. It gives us two possibilities. Either this number is 1 or it is 2. But we have something else which we have so far not used. It's the fact that the group has odd order. But we also have this, of course, or to be more explicit, K, which is the order of the group. Since K is odd, and hence the GCD of K and 2 is 1, we must have this fact. It's like that thing where we used the fact that the GCD of 28 and 65 is 1. It's like that because because K is odd, 2 does not divide K, and this fact leads to this equation that the GCD of K and 2 is 1, or in other words that they are relatively prime. But then again you would find some integers, say alpha and beta, such that alpha K plus 2 beta is equal to 1. So using that equation and these two divisibility relations, we get this. And now we can conclude, hence this order is equal to 1, but we already know that in any group the only element of order 1 is the identity element. This implies that this is equal to, we already have this, okay, so very nicely we already have our E, and that's how the solution ends here. And let me just end the video also here. We are going to continue with the coming other exercises that we have after this in the next Lee update. And tomorrow, of course, we are going to go back to real analysis, where we are going through the notion of countability, countable sets, at most countable sets, and things like that. So with that, I just wrap things up. So see you tomorrow with real analysis, countability. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.